So today we're going to be wrapping up our section on processes and really the first half of the class on system software, actually using and programming system software. Today we're going to go over shells, but really it's going to be about the project. This project is going to be a little bit more substantial than the file system project because you're going to have to do all the piping and redirecting, fork and exec. The code is not that long, but it is a little tricky. And I'm going to show you how to process the input and actually give you examples of writing code for this project. Next week is our midterm. That came really fast. That's like halfway through the semester already. And so on Thursday, we'll have a review session. There won't be like an exact practice exam, but I'm going to basically tell you all the content that's going to be on the exam. We'll go over example questions. And it's really just going to be drawn from homework, lectures, and programming projects. But I'll give you more details on Thursday about like the format. It'll be in class, in person, but on web courses. I'll have backup paper exams just in case. But yeah, this is kind of the current state of doing exams in this class. Yeah. No, it won't be locked down, but we'll have proctors here. So you can only have web courses open. You'll have paper notes, but it'll be in person here. Yeah.
So wait, what are we allowed to have? Because I remember you mentioned something about paper notes in a previous class.
What, say again?
There was a previous class you mentioned being able to use.
Yeah, you can bring paper notes,
Okay.
but not electronic notes.
Are we allowed to print out our electronic notes and bring them on paper?
It should only be on paper. It should only be on paper. Yeah, so you can bring physical pages. So you'll bring your own laptop, but on your screen will only be web courses, only the exam. And we'll have proctors around to make sure. Yeah.
Can you define by reasonably sized?
Some people have just sort of joked about like printing it really tiny and bringing like a magnifying glass to kind of like work around the page limit. So I guess I'm the arbiter of reasonableness now. But I don't know. Most people seem to think that this was sufficient notes for the class. But you'll see during the review, I think. And when using like APIs and writing C code, you don't have to be like 100% perfect. Make sure, as long as you have the algorithm right, the right syscalls, that's what we check for. But all right, well, we'll have more information on Thursday. We'll have a review in class. It'll be recorded. And then, all the format, number of questions, and everything will be there. It'll be a mix of multiple choice, open-ended, and short answer. Okay, so that's wrapping up the first half of the class. Questions on anything from last time on piping? I know it's getting more complicated, right? There's combinations of syscalls. Each syscall itself is pretty simplistic in what it does, but bringing them all together, there's kind of a lot of bookkeeping. There's a lot to get right to make these work. Questions on piping or anything on processes or anything up to this point in the class. Logistics, FS project. Oh yeah, FS project is due on Thursday as well. Questions? What questions do you have so far? All right, let's go over the homework. So hopefully it's a little redundant by now, but when you go to exec a new program, even if you fork a process and exec a new program, how come you don't, you can just use the standard in file descriptor, right? It's like standard in _ file number. Why don't you have to open that file? Yeah.
It's automatically opened on the program initialization.
Okay, it's opened. It's automatically opened. Who opens it? Who opened that? So you have a running process. You run your Hello World program. Who opened that standard in?
Process scheduler open?
Well, not quite. How did you run your program? How did you run your Hello? Bash. You ran it with Bash, right? And so generally speaking, it's whoever called exec for your program. So in the case of Eustace, you log in. That SSH daemon calls Bash on your behalf and pipes that terminal input and output to the Bash program. And then with Bash, bless you, Bash, you can run other commands. And we're actually going to implement a command line processor for our next project. And that's what calls exec. And when it calls exec, that has the freedom to change what standard out is going to be. That's what. And so how do you change What's one way to change standard I/O, like what device or what file is opened for that standard out? How can you do that with a syscall? What's that? Dupe, yeah, exactly, dupe. Dupe was the syscall we use for redirection. Okay, any questions on that? Any questions on number one? So just another question on another way to phrase standard I/O. What files does standard I/O comprise? Good, yeah, in, out, and error, standard in, standard out, standard error. And this is just a question, next one is just a question on piping. So write a bash command that uses ls-l and grep to find lines matching RW as a single pipeline. So just a little quiz on grep and piping. So how might, there's nothing in here, let me go to this directory. So how might we write this command? Anyone want to give an answer? Okay, ls-l. Yeah.
And then you use the pipe and then grep
Pipe.
RW.
Quote RW. Yeah. That's it. So it's just saying pipe between the two commands, and that's how you use grep. The first argument is the substring you want to match, or really the regular expression you want to match. Questions on this? Just a review of how to use pipe. And then the last one was write a snippet of code, and I meant C code here, to create a pipe between two processes that redirects one standard out to the second one standard in. Use any programs you like. So in other words, you can run any programs you want. This is just a review of the code example from class. So this is filter.c does this exact thing. Creates a pipe. What's the syscall for creating a pipe? Pipe, yeah, it's just pipe. All you do is create that pipe, call fork and exec on each process, and then do redirection using dupe2. You redirect the left program, the first programs, redirect it standard out to the in end of the pipe, the right end of the pipe, and then redirect the standard in of the second program from the read end of the pipe. And that code is here. So it's really just this code. It's for that answer to that homework. Questions on that? Anyone want any review of piping? Everybody good on piping? So you'll actually use it in this next project. All right, any other questions? What other questions do you have about homework, processes up to this point, FS? Okay, everybody's, oh yeah. Does what have to be in the same order? For the FS, no, the order doesn't matter. The order doesn't matter, yeah, order doesn't matter. So if you look in the test scripts, I pipe to sort, which makes sure all the outputs are sorted, and then they'll be comparable, yeah.
I know that for the extra credit, there's something where it shouldn't matter what order you give the arguments in.
Yeah.
Do you have to do that for the non-extra credit part?
Well, the non-extra credit part, I see what you're saying. So the non-extra credit part, there's only one order for the optional arguments.
Okay, so if we don't do the extra credit, it should always be either -L and then directory or just the directory?
That's right, yeah, it should always, yeah. So the question was about FS project and the order of these arguments here. So I think typically, although this might be only my limited understanding, but typically options are before. These are called the optional arguments. The ones with dashes before them are by convention the optional arguments, and then the ones without dashes are the positional arguments. That's like argv1, argv2, argv3. So my understanding is that the optional arguments would always be before the positional ones, but lots of commands actually take these in any order. But this usage here, these brackets mean optional. It means they don't have to appear here. So yeah, the order will only ever be -L first or path first. So that kind of implies a pretty simple algorithm for processing these arguments, right? You just check, does argv1 start with a dash? If it does, then make sure the second character is L. Otherwise it must be a path. But yeah, good, subtle question. Questions on that? Any other questions on this? So I've got like nobody in my office hours about the FS project. Is everybody like great on the FS project, or you're just procrastinating till like the deadline or to the end of the semester? I can't tell. All right. So if there's no other questions, let's take attendance and then get into the shells. How to write shells. Okay. So let's go to our last topic for processes. And this is on how shell processors actually work. So this command line tool that you're using every day, at least in this class, is a piece of software that somebody wrote. It's a piece of system software that somebody wrote. And I think it's called a shell. I don't actually know why, but I think it's called a shell because it's like a thin wrapper around the operating system, around the kernel. We learned about all the APIs and some of the abstractions, process abstraction, file abstraction, and all the API calls that we can use to work with those abstractions. And that's what's exposed to you. That's what's exposed to you by the kernel developers. And a shell is like a thin wrapper around that. So you have access to all those calls through the shell. So the command line interpreter takes in commands as input. So for instance, ls space dot slash. And it runs them, so it interprets them. It's like Bash is a programming language under the hood. It has a kind of a full programming language. But you can think of it as something like a language. It takes in this text and interprets it. So commands in this language are just strings. And in C, what are strings in C? Arrays of characters, right? They're just character arrays. And what are characters? Typically in like the C world?
ASCII integers?
Yeah, they're ASCII. They're really just integers. So a character is really just an 8-bit integer in C. So under the hood, it's really just an array of 8-bit integers. And I think we covered this a little bit, but the representation of strings in C and kind of in the Unix world is in ASCII. There are other encodings like the UTF encodings and IPSDIC, but we're only going to be dealing with like ASCII strings. So strings are really just arrays of characters, and characters are just numbers, but they are used to encode symbols in some alphabet. So for ASCII, the kind of very old standard, it's only 8 bits. It only has 27, I think, characters, which is not 8 bits, right? That's 7 bits. So each letter, like A or B, these are encoded with a number. And also, perhaps confusingly, the symbols, the ASCII symbols for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, these are not the same as the integer 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for instance, the ASCII code for the symbol 0 is 48. But that's not the number 0, right? That's not the number 0 in the machine. And same with all of the other digits. All right, so any questions about strings in C? I know you probably learned about this, but under the hood, these are really just strings of characters, and it's up to the software that you use to interpret those ASCII numbers as glyphs, as pictures on your screen. So that's why if we take this, say, C program, and when I use cat, it writes out that data in my terminal program interprets those as ASCII and draws them on the screen for me. But if I look at use a program like hexdump to look at the contents of this file, if I look at the contents of this file with hexdump, this -C flag, capital C, will put the hex representation of the file on the left, and it'll put the ASCII interpretation of that file on the right. On the left, you can see the hex codes for this file is just numbers. It's just like any other binary or image data. The file is just stored on disk with bits, with binary data. And if we kind of unmask the ASCII representation, we just see integer values, here represented in hex. Yeah.
So I know for like on Windows and Mac, like modern day, like they're just kind of like more graphical, but they're still talking with the shell and like the actual like terminal. How does like it convert from clicking on like on a, like the file like folder on my computer? So like how does it talk to the shell and like display my files onto there?
Oh, well, so the question was about how does the windowing system interact with the shell?
Yeah.
So I think these days the windowing system is the shell, basically. So it's directly implemented on top of the kernel. So it's not going through, say, PowerShell or Bash. There were older windowing systems that would do that, where the windowing systems in Linux were just a wrapper around command line programs, and they'd issue commands. But that would just work with the same tools that we have. You could just execute a program under the hood. And there's even a library call for executing a shell command if you really want to. But no, modern windowing systems are their own shell. They don't need a command line shell to run. So those windowing systems, will just directly call the kernel. In Windows, at least old Windows, I think it's probably still true today, the windowing stuff is part of the kernel, is part of the Windows kernel. So like drawing windows, creating windows, moving them around, that's at the kernel API level. But anyway, this is a bit of a tangent. This is more of an OS design question. But yeah, so the windowing stuff is basically a substitute for the shell. And it uses the underlying kernel calls to do, run programs and open files. But hopefully you can imagine, learning about the shell, you could write your own graphical shell, your own graphical interface. Actually using the same techniques we're going to have here, you just replace the part that processes user input. Instead of processing text input, you would process like mouse movement and image output. But under the hood, you would just use the same kernel calls to run programs, open files. Okay, questions on strings, C-style strings. Hopefully that's most of the review. Okay, so you can think of the bash program, a shell interpreter. It's really just a program that takes in strings, and its output is calls to the kernel. That's really all it does. So when you type on the command line, you're just typing in ASCII strings, and it's up to bash to give those symbols meaning, because the pipe symbol has no intrinsic meaning for pipe. So under the hood, you call the pipe syscall. But that vertical bar does not in any way imply the pipe syscall. It's the bash interpreter that takes that symbol, that ASCII symbol, and says, okay, I've seen a pipe symbol. The user wants me to create a pipe. And so the program you write, your command interpreter is going to look for that symbol and then actually call pipe and actually run the programs and call pipe on your behalf. So this is true of any language processing system. Once we get into the compiler half, this will become a little more mind-bending, but I think this is a good sort of intro to language processors. And this is kind of true, well, maybe true in all language, depending on your philosophy. But if you think about words or pictures or representations, if I have a photo and I rip it, I'm not going to actually cause an earthquake or kill that person in the photo just by ripping the photo, right? Because the photo is just a representation of the person. Same thing with words. So if you say a word, it just represents something. It isn't the thing itself. This is called the map territory problem. And so when we write software that interprets a language, we are the interpreter of that, or our program is the interpreter of that language. So we're going to write code that's going to take in these symbols which have no meaning, and it's going to give them meaning by taking some action. In our case, it's going to see a pipe symbol, and it's going to take action by actually calling the pipe syscall to create that pipe. Okay, so yeah, map territory problem. You'll sort of understand as we get into how we actually process the input. So we can kind of break down this interpretation into two steps. First, we parse or collect the input from the user, and then we take that input. We're going to make an in-memory data structure to represent that input, and then based on that user's input, we're going to take some action. We're going to run action on that. So that might be the user gave us a string. by itself, and we're going to say, okay, if it's a string by itself and it's not a pipe, it's not a redirection, then I'm going to interpret that as run this program, given this name. So this is an example when I ran ls here. That ls is just an ASCII text. It doesn't imply anything about forking or execing. The bash program reads that in, sees that the user has given it just a string without any special symbols, and says, okay, I've seen a string without special symbols, so my interpretation of that is to call fork exec on that program name. Kind of makes sense? Okay, so in order to process this input, we need to be able to pick out the words or the tokens from our input. Has anyone heard the word token before? Tokenizing input. Okay, a little bit. Did you learn about this in like CS1, CS2? No? Yes, no? They talked about it. Some people are saying yes, some people are saying no. So tokenizing the input or processing the input is akin to just picking out the words in the input. So if you think about, say, written English language or spoken English language, if you're not familiar with a language or you're learning a language, it might be really hard to pick out individual words, right? So if you've ever tried to learn a language. So I'm just speaking continuous sounds. When I say continuous sounds, it's sort of hard to tell the difference between the S in continuous and the S in sounds, right? It could be one word, it could be two words. So the first step of processing the input is to figure out what the individual words in the input are. So for instance, if I have this command here, ls space dot slash space dot dot slash, how many words or how many tokens do I have in this command? So some people are saying 3. Why? Why 3? Yeah, why 3? What was that?
Did you start with word and just 2 spaces?
Spaces, okay. So in this language, spaces are a delimiter. They indicate boundaries between words in our language. So even though this looks like nothing, this is actually a space character. These are space characters here. So when processing this input, we're going to define a language where we have strings of characters without spaces are one word, and spaces don't have any meaning in our language. They're just used as delimiters. So if we define this string a little more precisely, if we say, well, these are strings without spaces, then you could imagine writing a program that just loops over each character one at a time and is able to break up the string into spaces, or break up the string into tokens. So that's pretty straightforward to do if you just say, well, okay, whenever you see a space, break up characters in the input. And in this case, that would give us these 3 tokens in our input, these 3 words in our input. Sort of makes sense? Questions on that? So you can imagine writing an algorithm like that, right? Just loop over each character in the string, look for a space. If you see a space, start a new token. Gets a little trickier when, say, we've got symbols like redirection. So if I do this for redirection, bash allows us to omit the spaces in this case. So I can say ls angle bracket ls.out without spaces. Why is that? Why is it that I can omit spaces doing that, whereas if I omitted the spaces between ls and ls out, I wouldn't get the same thing? Why is it that bash can tell the difference between no spaces here versus no spaces here? What's the difference between those tokens? Yeah.
The redirect character is used that in the
Yeah, the redirect character. So we can say, well, all right, if we see an angle bracket, then we don't actually always need spaces. If we have a well-defined, if we have a clear definition for what each type of symbol comprises, what characters each symbol comprises, we don't have to only rely on spaces. So we can say ls program names are any string that don't have a greater than sign, a less than sign, a pipe symbol, a space. If we define it that way, then you could imagine writing a program that just loops over each character and says, all right, if I see a string of characters that's not an angle bracket, that's not a pipe symbol, then I'm going to group those together in a word. If I see an angle bracket, I'm going to group that as its own word, and so on. And I don't need spaces in that case. I just need a good definition, or a kind of unambiguous definition of what each token in the language looks like. Questions on that? That sort of makes sense? Could probably sit down and imagine writing an algorithm for doing this if you had a really clear, specific definition of what each of these symbols looked like. Okay, so I already went over some diagrams of this. Same thing with piping. So these are just, I mean, hopefully you're all familiar with Bash at this point, all the symbols in this language. Yeah.
So I'm assuming we're just be doing a lot of like string compares to see like, or would we just be comparing character by character?
So in the actual project, I've given you a tool that will actually do this for you automatically.
Oh,
It's called Elixir. That's what I'm kind of what I'm getting to. So it's kind of a pain, or it's not only a pain to do this by hand. Well, check each character one at a time and account for all the different types of characters you can have, types of tokens you can have. It's been formalized. So if you anyone take discrete 2 yet? Did you talk about regular expressions or finite automata? So you'll get to this when you get to discrete. Did they cover this in discrete 1 at all? Automata, finite state machines? So this has been so well studied that you don't even need to write this kind of code anymore. You can actually just write the description of what these tokens look like, and then a Elixir generator will automatically generate a C program for you. I can actually show you what that looks like here. There's a program that will take definitions of tokens and automatically generate a C program that does this for you. That's how well understood tokenizing is. So I'm not going to make you write this. Instead, we're going to use it. But you still need to understand the concept of tokenizing, that you have a string of characters, and you need to pick out the individual words in those characters. And once we pick those out, then we can start ascribing meaning to these characters. Okay. So for the input, I didn't actually tell you the process yet, but we're going to be doing redirection, piping, and running programs. So what different types of symbols do we have? What different types of tokens are we going to have in our language? So we saw redirection, right? We saw redirection. We saw strings for program names and arguments. What else do we have? We had piping, right? So we can list out every possible type of token we're going to have in our language. The program, the Bash interpreter or the shell interpreter we're going to be writing here has a pretty small set of symbols that we're going to use in the language. So if we see an angle bracket, that's always going to mean the redirect in-out symbol. If we see the left angle bracket, it's always going to mean redirect in. If we see the pipe symbol, this should be vertical pipe, not slash pipe. It's supposed to be slash vert. I forgot to. I put the wrong symbol there, but this should be a vertical pipe. If we see a new line character, that's going to be the end of the input. And then finally, if we see a string, and I'll show you what the definition is, but it's basically alphanumeric characters plus a few other symbols, that's going to be a string in our language. So questions on this? These are all the 5 types of tokens that we're going to have to deal with in our Bash input. Questions on these? Yeah.
So I assume the hard part is just like kind of like guiding through the string path to the program in this project.
Guiding, say again?
The string, like when you're given the string, is trying to find the right program.
Exactly. Well, no. You mean once you have the string, the first hard part is going to be figuring out which part is the program, which part is the pipe, which part is the redirect. And I'm going to give you some tools to help you do that. But then there's an additional problem is, even if you see a pipe symbol, what if it's a pipe symbol by itself and there's nothing after it, or you have 3 redirect symbols in a row? So the first step is taking the words. The second step is figuring out how they relate to each other. So a pipe symbol should always have 2 programs on either side of it. A redirect symbol should always have a file and a program. You should never see 2 pipes in a row, etc. So there are rules that are above just tokens, called grammar rules, that we're also gonna get into here. But let me fix this input. Yeah, so now it's a pipe. Simple. Okay, but let's get there. So, okay, what about white space in Bash? Does white space have any meaning in Bash, or at least in our language that we're looking at here? If I, for instance, put a huge amount of space between the redirect and the file name, in Bash, it doesn't really have an effect in Bash. In the same way I can put no white space, I can put an arbitrary amount of white space there. Now, strictly speaking, in Bash, you can have files with spaces in them. You can escape them. You can put them in quotes. We're not going to deal with that here. That makes lexing and parsing a lot more complicated. But for the most part, space is going to have no meaning in our input language. It's just going to effectively delineate tokens, delineate arguments. Okay. So as I was mentioning, even if we're able to identify all the tokens in our input, is this a valid Bash command? Why? Why is it not valid? Yeah, there's no argument on the other side of the redirect. So there's some. So just like in this is kind of a little preview of what we're going to be talking about when we talk about compilers. But just like in human language, it's not enough to just know the individual words in the language. So this is a classic example from Noam Chomsky's work. He compared two sentences that are semantically, he asserts, meaningless. And let's look at these two sentences. So one is, furiously sleep, ideas green, colorless. And the other one is, colorless green ideas sleep furiously. Which one kind of sounds better or sounds more right? The first one, right? Even though you may not know what a colorless green idea is, I mean, it's literally contradictory semantically. There's some sense that this is correct somehow. And at least his position, and what we're going to use in this class, is that this is grammatically correct. That the position of these words could have some meaning in our language, whereas in this one, it doesn't. So this has, subject, verb, and adverb in the order that we expect in English, at least. And it's the same thing in Bash. So I could say, ls, I could say something like this, and all of the words are right? I have a redirect symbol, I have a pipe symbol, I have a program name, I have a file name, I have another program name, and it doesn't have any meaning in Bash. But if I just rearrange these characters, well, now it works, right? It works. So while lexers and, tokenization will give you the individual words in the language, we need some other definition in order to know how these words should be arranged. And that's called the grammar. So the grammar of the language is a definition of how words should be ordered in that language. And I'll get into this a little more when we talk about compilers. We're going to have to learn more about grammars. But I wrote up here a grammar that I'm just kind of try to intuit our way. We're going to kind of intuit our way through this grammar for our Bash interpreter. So basically, the way the grammar works is we've got all of our tokens here, like new line character, pipe, string, redirect symbols. So those are our tokens from the language. So we know what those are, right? They're just like sequences of ASCII characters. Yeah, go ahead.
Do you ever, in the kernel,
Yeah?
I don't understand the difference between your piping after I think writing is the right term, but the greater than sign, yeah.
Oh, the fact that I'm piping into ls?
Yeah, well, the fact there's the line, I don't know why it's before the ls, or it's maybe after, not before the ls. No.
Well, this is the pipe between two programs. Say again? This is piping between ls and wc.
Oh, yeah.
I'll just quickly, just to make sure everybody's on the same page, let me diagram this one. So this will give some hint as to syntax, actually, how grammar works. Okay, that is extremely annoying. That is very strange. Uh-oh. Okay. Okay, so what words go together here? So as we talked about this, so these are the tokens, so hopefully we all are on the same page about the tokens. Let me use another color here. So these, I think we can all agree, are the individual words of this expression to bash. But which of these symbols go together? So we know that this redirect, the reason the previous command didn't work is because the redirect symbol is expecting a file name after it. So we know that these two go together somehow. We know that these mean a redirect in. Right? Kind of makes sense? And now, does this redirect refer to WC, refer to the pipe, refer to LS? Which one does it kind of operate on? LS, right? LS. So we know that somehow this LS program name is connected to this redirection. So this is I think, what did I call it in my grammar? I think I called it a command. So we can say that this is one bash command. And then what about this pipe? Does it only operate on WC? Does it operate on LS? The pipe, yeah. What is it? Yeah, it operates on WC for sure. Yeah, and the whole exactly, the whole first command, right? Not just one piece of it, the whole first command. So if I say something like, I visit the store, and I say, I, after talking to my friend, visit the store. Who's visiting the store, my friend or me? I, right? But textually I said, I, after talking to my friend, visit the store. So friend is close to visit, but we're not confused that it's the friend going to the store, it's me going to the store. And we'll see that, again, we'll see that more. I'm kind of previewing the compilation stuff. But this entire command is the left operand of this pipe symbol. So this is called the hierarchical syntax of the language. And again, we'll get to that more, but I just want to make it clear that what the meaning or what the syntax of this command should be. So this redirect symbol is operating on the file name and the program. This whole thing is one command, and the pipe operates on two commands. So just to make clear, that makes sense, right? Makes sense. So we can express, and now, if we write, we have lots of different ways to write a valid bash command. We might omit the redirect, we might not have a pipe, we might have another pipe, we might have 10 commands. They all might have redirects, they might have arguments. And we can, that seems like an infinite amount of possible commands. And actually, strictly speaking, there's an infinite possible number of commands here. But we can capture a definition of all possible bash commands using a grammar. And so I'm going to kind of intuit through this grammar here. We'll learn more about grammars after the midterm. But all this is saying is, here is how you construct each part of the language, just like sentence diagramming. Here's a noun phrase, here's a sentence, here's a verb phrase. They have this hierarchical relationship. So here we're just saying if we have a redirect in, it's the redirect in symbol followed by some string, to represent the file. If we have a redirect out, that's constructed of the right angle bracket followed by a string, which we saw here, right? We know kind of intuitively that this redirect symbol should always be paired with a file after it. And so we can capture that definition like this. We can just give a new name to the grammar construct, even though the word out doesn't appear here. Well, this does appear here, but even though the symbol of out doesn't have to appear here, this could have been something else. This could have been text. And this word out doesn't actually appear, whereas this symbol actually appears there. Yeah, question?
For the first three pipes, new line, command, pipe, command, what's the difference between those three?
Let me get there. I'll get there. So hopefully this sort of intuitively makes sense, in and out, right? And then similarly, a program is really just the program name followed by star here means 0 or more strings. So when you call a program in Bash, you say ls followed by some arguments. And so it's just, a space delimited sequence of strings. So that's all string, space, string, star means. And then a command, as we saw, is a program. So remember, a program is just some sequence of strings, one or more strings, followed optionally by a redirect in and a redirect out. So question mark here just means optional. That symbol, the symbols may appear or may not appear. And then the first three are maybe a little bit more confusing. So the whole command, which I call start, is some series of piped commands followed by a new line character. Pipes is some single command followed by 0 or more pipes. And then a pipe is the pipe symbol followed by a command. So you can imagine that this is repeating any number of times. So if I have this, so this allows us to capture, because pipe star means 0 or more, this captures both single commands, it captures 2 commands, it captures 3 commands. That's what that pipe star represents, that we can have any number of pipe command strings after a single command. Does that kind of make sense?
Yeah, it's redirected to the pipe, and pipe star is redirected to the below.
You can think of this pipe name. So if you see how pipe here, so in here, so this is used here. It's almost like a function calls. You can think of it as like recursive function calls. The in meta symbol here is defined on this line. So yeah, wherever you see in, you can imagine substituting this rule here to figure out how to parse that. And so for pipe, this is 0 or one time, and then this is 0 or many times. So you can imagine copying in or substituting in pipe command here 0 or more times. Yeah, sure, yeah.
There's sometimes when I'm typing on the terminal and I accidentally hit enter, but I don't put in the rest of the argument, it will still let me put the rest of the argument on the new line.
Yeah, that's probably because you're putting a quote character. Yeah, if you put a quote character, it'll try to process the whole quote. I'm not going to get into quotes and stuff like that. The processing is a little more complicated. It's a little more annoying. But basically, you can put in white space in quotes, including a new line character. So that's why it allows you to do that. You're just putting in a new line character.
But we don't have to worry about
You don't have to worry about any of that. I've given you a much simpler definition. I've already defined the tokens for you, and then you'll be writing a parser to actually collect the input, what the input is, and actually, this is basically the next step. So anyway, so this is the grammar. Questions? I know I haven't gone into detail in grammars yet. We will see that more, but sort of intuitively, do you get the idea here? So you can, if you think about human language, this might be paragraph, this might be sentence, this might be noun, verb, object. So you can imagine writing if you wanted to write a definition of what all inputs looked like, this is one way you could do it. You could formalize it. You could make it a mechanical definition of that input. Questions on the intuition behind this? Okay. So I basically went this over already, but you can read this special equal sign as this part of the expression can be constructed by the right-hand side. So we can make an out redirection by taking 2 tokens, taking a greater than angle bracket followed by a string. Also notice one thing here is that, I probably have a good example in next time I come back. But notice here that string is used multiple places here. It's used to mean the program name, it's used to mean arguments. It's also used to mean files for redirection. So this is also what grammar provides. It implies some difference in semantics. So even though we might have the same word here, the same word ls, so I could say, for instance, ls, ls, ls. The first ls here is a program name. This is an argument to the program. And this is a file to redirect the output to. So just like in English, you have overloaded words. Like the word plus can mean addition. It can mean also. Okay, anyway, so that's grammar. I just want to give you the intuition behind grammar. So this is some little pseudocode for processing the input as a series of tokens. And I'm going to write some code examples for this as well, actually. But basically, all we need to do to process this grammar, to process the input, we're going to read in the first command as just a series of strings, and then we're going to see if there's a redirect in, read those tokens in. We're going to see if there's a redirect out, read those tokens in. And then if we see a pipe command, we're just going to repeat. We're going to consume that pipe command and then start back up here at command, reading in a new command. So the pseudocode on paper is not super hard to write, even though this grammar looks kind of complicated. It's really just read in a program, check to see if there's a pipe character. If there is, read in another command, check to see if there's a pipe character, read in another command, and so on. So you can imagine writing this with some while loops. But all right, let me, I'm going to actually write you some code. So let me make sure I have time to get to everything. All right, I'm going to skip ahead to actually just writing some code. I'm going to show you the beginning of writing a parser for this bash language. So I'm just going to give you a quick overview of the code we have. I've given you the Lexer code already. So here's the project. This is some code that will give you the starter code for this program. So I'm just going to quickly download this. So here's our starter code. I'll let you guys kind of explore the code in here. Lex.l is our token specification. So don't worry too much about the meaning of this, but you can just see there's a little definition of what each of these tokens are. So it just looks like our table where we've got a pipe symbol and it returns the name pipe for it. But don't worry too much about that. What I've given you is some template code and some helper code in util. This is all documented in the proc description, so you can review it. But I've given you a command called consume that will read one token from the input. And the way it works is it just sets these global variables. So when you call consume, the next token from the input the type is going to be stored in lookahead, and the actual text of it is going to be stored in lexeme, which is like the technical name of the text of it. I've also given you some helper code to help you match tokens so you can make sure that you actually get the token you expect in the input. And there are two. Actually, this is probably better shown in my slides. So these are the names of the tokens in C: string, pipe, redirect in, redirect out, end of line. These are the global variables that store each token when you call consume. I've already kind of gone over an example of this, but when you call consume repeatedly on this input, you're going to get a string token whose lexeme is ls. Then you'll get a redirect out token whose lexeme is the angle bracket. You'll get another string whose token is ls.out. You'll get a pipe token whose lexeme is a pipe symbol. And then you'll get another string whose lexeme is wc. So I know that's like a fancy word, lexeme, but questions on this? So this is what's going to happen if you use the code that I've given you and you call consume over and over and over until or you call consume 5 times on this input, these are what the values of look ahead and lexing are going to be, if that makes sense. So it's automatically tokenizing for you, and you'll get each symbol one at a time. Yeah.
And it knows when to stop and it's like, no more.
Well, it'll keep reading until you stop asking for it. So, oh yeah, it's a good question. So how do you know when to stop? Which I think I gave you code for this already, but if you look at the definition of the language, the last thing in the language, oops. Oh. Where's my grammar? The last thing in the language is a new line character. So once you see a new line character, you'll know that you're done processing the input. And I think I've given you code for this, so you don't have to guess at that. So I've given you 2 functions to help you match tokens. So one is called ensure, and you'll give it the look ahead token and the token you want to match. And if it doesn't match, the parser will just fail. You can just quit immediately. So if the input's not grammatical, if it's not a valid input, you can just quit. And one is to check whether 2 tokens match, and it'll, same idea, but it'll return true or false if they match. So this is used for, say, redirect, when you may or may not have a redirect. This allows you to check conditionally. All right, so let me actually write part of the parser for you, and we'll walk through what that looks like. So this is not the complete parser, a part of the parser. So here's how it looks. So I've used C's statement labels in order to indicate what part of the grammar I'm processing, but it's optional. You don't have to use those. So the first thing I do in the parser is to call consume. That'll bring in the first token from the input. So if I have this example ls angle bracket ls out, consume will read in this first token here, ls. And then to make sure that the command is valid, the first thing should be a string, right? It shouldn't be a redirect symbol, shouldn't be a pipe. The first thing in the command should be a string. So to make sure that it's the case, you can call ensure look ahead. So it's going to take 2 tokens. One is the look ahead token, that's the output of consume. And the second is the name of the token. So string is the name of the token. And I can do the same thing for, to be pedantic, I can do the same thing for program. But then once I've assured that I've seen a string for my program, I can call consume to get the next token in the input. So let me get back to the grammar to show you how this corresponds here. So once I'm on a program, the first thing in a program should be a string. And then you can imagine how you might capture 0 or more. You can just write a while loop and just say while match string, keep reading in strings in that input. So question so far? I'm just reading in one token at a time and just checking it against this grammar specification, making sure that I indeed have a string. So once I've captured all the strings from the program, the program name and the arguments, optionally I can have redirects. You don't always have redirects, but some inputs will have redirects. So if I'm trying to check whether there's an out redirect, I can use match to check whether my next token is a redirect out symbol. This is how you do it, match this. Then I get the next token, and my next token should be a string, right? Because if I've read a redirect out, then the next symbol must be a string, so you can use ensure to guarantee that. And then we continue reading input. Questions so far on this? So it's just moving up from the character level. You can imagine when you're writing a lecture, you just check one character at a time. Here we're checking one token at a time to make sure, yeah.
How does consume get, how does consume get the string?
So the lexer, the generated lexer will, when you call YYLex, it'll give you the next token, and it'll put the text of that token in a variable called YYText. And so, yeah, this is gonna be, it's taken in from standard in by default, and it'll just take each token from the input for you. So this consume will automatically tokenize this input for you. And each time you call consume, you're going to get one token from that input, the next token in that input. So think of it like reading one character at a time in a character array. You just loop over each character in the string to figure out what your words are. Here we're looping over each token in the string and checking what kind of token it is. Okay, so here's how we implement out. So because out is optional, we use match function to check whether this is the redirect out token. If it is, then we just read in the string and make sure the next character, or this token actually is a string. And then finally, at the end of this, so I haven't implemented the full parser for you here, but at the end, we should see an end of line character at the end of whatever the end of our command is, should be an end of line character. Okay, so I know this is very intuitive, and this isn't a complete implementation of this, but the main point I want you to get is, every time you call consume, that's like incrementing one token in your list of tokens. And you use match and ensure as you consume tokens to make sure that the input has the right sequence of tokens that you expect for your command. So if it doesn't, if the user ever says something like, if they ever say something like this, you don't have to process it. You only want to process it if the tokens are in the right order of input that you expect. So you can demand that from the user by using ensure. When you say ensure, you're demanding. It's like assert. You ever use assert in CS1, CS2? It's like an assert for the input. Okay, questions on this so far? Yeah.
Do we care at all about what the strings are themselves, or do we just care about the matches, the general?
So at this point, no. It doesn't matter at this point. So just like colorless green idea, sleep furiously, it doesn't have any meaning, but it has grammatical sense. Here, at this first stage, we just make sure the grammar is right. So if I say a program that doesn't exist and redirect to a file that I don't have access to and pipe it to a program that doesn't exist, this is still grammatically correct, right? The tokens are in the right order. So even though it doesn't semantically make sense, it's in the right order. So this is the first step in any language processing. So remember, I broke it down into 2 steps. Process the input first, and then interpret the semantics, interpret the meaning of it, and run the programs. So separating it out just makes language processing much, much easier. Okay. So as written, all this program will do will guarantee that the input matches our grammar. By having these ensures here, it'll just make sure things are in the right order. It won't actually do anything with that input. So let me show you some examples. So here's running the program with that parser. If I type in a string, then I don't get any error. But if I just type in, say, a redirect symbol, I get a parsing error, right? Because just like in Bash, you can't just have a redirect symbol first. You must start with a string. So this code ensures that. So it guarantees that the first token is a string. And then only then does it continue on reading the next token and then checking for a redirect. So now this program will also not work for redirect in because I haven't actually written code to do that. So that'll be like your next step. So the next step you could do is to look at the code for redirect out and try to write something similar to be able to match redirect out. So that might be something like this. It should be a redirect out token followed by a string. So now if I try a redirect in, I don't get a parsing error. And in fact, I can do both a redirect in and a redirect out without an error. So here I get a parsing error when I have, like, let's say I want to run, ls-l. That should be a valid program, right? So why does this parser not recognize ls-l as a valid command?
There's no support for flags.
Well, it's not just flags. So if I say ls dot, I get a parsing error. ls root, I get a parsing error. So it's because here, the command only reads in the first program. It only yeah, go ahead. Sorry.
In your defined grammar, you have a program has to be followed by either.
Yeah, a program could be followed by 0 more commands after, strings after it. So here, I would need to write a while loop to read in and consume strings. As long as I'm seeing strings, I should consume them as the arguments to my command, and then move on to redirection. So same thing with pipe. Pipe is not going to work here because I never actually process pipes, even though this should be a valid one. My parser doesn't actually implement it yet. Okay, so hopefully that'll get you started on parsing. I know you may still have more questions. Ask on that step. We can talk about it next time and during class. But yeah, I just want to give you a little exercise of processing the input. Okay. All right, so notice that this program doesn't actually do anything yet. It just checks that the input is valid. So in order to actually do something with this input, the parser doesn't actually output anything. It just makes sure that the input is valid. If we want to do something with it, we need to first actually collect the information from the user. So I've given you a struct that will store these commands for you. So it's a linked list of commands, and all it is just the list of the arguments and optionally any redirect in or out files. So just like in when you get argv from your input, it includes the program name. Same thing here. So the argv includes the program name and all the arguments. So all we need to store is the program name and all the arguments, and optionally in or out redirects. Questions on this data structure? So it's everything you need to be able to run your command, right? You just need the program name, arguments, and then any redirects. And we've got a next pointer here because this is just a linked list for the pipes. Questions on this data structure? So I've given you a bunch of code to add to this linked list for you. So you just call the add command function and it'll create a new data structure for you. You just keep adding it, it'll add to the list. You can use print commands to help debug. And to read it, there's some global variables, first command and last command. So this is the first element in the linked list. All right, so let me show you how this program will be modified to use this add command. So here's our parser. So every time we see a command, we can call add command to add a new element to our data structure. And here, when we see the program name, which is what this first string is, we can start populating our data structure with the actual string. So lexeme is the actual string that got read in, and this is C for accessing the argv field and the first element of it. So the first element of the argv field is the program name, just like when you call exec or when you get argv into your main. Similarly, if we see a redirect in and we see the string, this string name, the meaning of that is that it's the out redirect file. So we can populate our data structure like this. Yeah? Yes, yeah. So if you have any invalid commands, you no longer need to try to run that program. That's kind of the nice part about doing parsing first, is if you don't have a valid input, you don't have to continue running the program. All right, so here's populating our one command with the name of the program here, because we read in the first token. The first token, if it's a string, it's the name of a program. If we see a redirect symbol, then the following token is going to be the name of the file. Same thing for redirect out. And then we can just call print commands to print out this in-memory data structure to prove to ourselves that this is getting the information as we expect. So it's a pretty printer. It'll just print out all the commands as a bash command. So notice it'll clean up any spacing differences you have. So if I've got difference in spacing, it will just print out each element of this struct for you. You can just use this for debugging. So questions on this? Questions on this so far? So I think it'll take a little bit to wrap your head around doing this, but start simple. Start with just a program and getting it interpreted when you just run a single program. But the goal here is just to take that input, tokenize it, turn it into this in-memory data structure that stores all the commands from the user's input. And then we're halfway there. We've processed our input. Then we're going to use that data structure to actually interpret and run commands from our input. Questions on this? Questions on the idea of this? Okay, so hopefully that code will get you started in processing this. And remember, go incrementally. Don't try to do all the parsing at once. Do it little by little and use the print commands to help you debug. And once we've got our in-memory data structure of all the commands, we can write our interpreter. So I've given you pseudocode here for you for your project. I'm just going to show you the code, actually show you the implementation of this to get you started. Here's the second part of our interpreter that just runs commands. Okay, so here's what it does. This is an example of just running one command in our list. So we just check to see if the first command is the last command. That's like in a linked list, how you check if there's one element in the list. So we take our command here, and the data structure is documented. The data structure is documented here. So we take our command, and how do we run a program in Bash? Well, we call fork exec, right? We call fork and exec. So here's fork. If we're in the child, we check to see if there's a redirect, and we can check that by inspecting our command data structure. If there's a redirect, we open that file and call dupe to do the redirection, just like we did in the redirection class. And once we do that, after we call fork, we create a new process, we call exec. And where do we get the name of the command? Well, the name of the command is in argv0 in the data structure. And that's it. And once we're in the parent, we only just wait for the children to exit. So let me just show you this code actually running, and you can see the beginnings of a command line shell interpreter. So I put ls in, it printed out my ls command, and then it actually ran ls in the output. If I do a redirection here, we don't see any output, but now we've created this my out file that has it. So that actually ran the redirection code here. All right, so I know it's going through this pretty fast at the end. This is code that'll get you started in writing this project, so you can look at this. But the main idea is you take the parser to process the input, put it into an in-memory data structure that just lists all the commands that the user wants. And then we have a separate function that just loops over or runs one of these commands at a time using the exact same code we looked at for fork, exec, redirection, and piping. And you just fill in that template. So if we want to know what file we're redirecting out, we just look at the command data structure to see what file the user asked for. If we want to know what program name and what arguments there are, we just look at that command data structure that we processed from the input. Questions on this? Okay, so yeah, bring questions next time. Ask on EdSTEM. We'll talk about this more as we even after the exam. All right, everyone, have a good rest of your week.